Good morning everyone, hello and welcome. In this video, we'll be diving into the fascinating world of particle physics and exploring the Standard Model, one of the most important and comprehensive theories in modern physics. The Standard Model is our current best understanding of the fundamental particles and forces that make up the universe, and it has revolutionized our understanding of the smallest building blocks of matter. So sit back, relax, and get ready to explore the amazing world of particle physics and the Standard Model. The Standard Model of particle physics is a theory that describes the fundamental particles and their interactions through the exchange of force-carrying particles. It is a quantum field theory that describes the behavior of particles at the smallest scales, and it has been very successful in explaining a wide range of experimental observations. The Standard Model consists of three families of particles, each containing a set of matter particles and their corresponding antiparticles, as well as force-carrying particles called gauge bosons. The matter particles are divided into two groups, quarks and leptons. Quarks are the building blocks of protons and neutrons, which make up the nucleus of atoms. There are 6 types of quarks: up, down, charm, strange, top, and bottom. Each quark has a fractional electric charge, either plus 2/3 or minus 1/3, and they also have a property called Color charge, which describes their interaction with a strong nuclear force. Quarks are never observed in isolation because they are always bound together in groups called hadrons, either as pairs, mesons, or triplets, baryons. Leptons, on the other hand, do not experience the strong nuclear force and are not confined within nuclei. There are also 6 types of leptons: the electron, the muon, the tau, and their corresponding neutrinos. Neutrinos are very liquid and do not have an electric charge, so they interact only weakly with other particles. The other leptons have a negative electric charge and are similar in many ways to the electron, but they are much more massive and took different lifetimes. The force-carrying particles in the Standard Model are called gauge bosons. There are 4 types of gauge bosons: the photon, the W and Z bosons, and the gluon. The photon is responsible for the electromagnetic force, which governs the interactions of charged particles. The W and Z bosons mediate the weak nuclear force, which is responsible for nuclear beta decay and other processes involving the exchange of particles. The gluon carries the color force, which binds quarks together in hadrons. In addition to the matter particles and gauge bosons, the Standard Model also predicts the existence of the Higgs boson, which was discovered at the Large Hadron Collider in 2012. The Higgs boson is responsible for giving mass to the other particles in the Standard Model, and it is a crucial component of the theory. The Standard Model is a complex theory that requires advanced mathematics to describe its behavior accurately. It has been very successful in explaining a wide range of experimental observations, but it has some limitations. For example, it does not include gravity, and it does not explain why the masses of some particles are much larger than others. Nonetheless, it remains one of the most important and well-tested theories in all of physics. The photon is a fundamental particle of the Standard Model of particle physics. It is the particle responsible for transmitting the electromagnetic force, which governs the interactions of charged particles. The photon is a type of gauge boson, which means that it is a force-carrying particle that mediates the interactions between other particles. In the electromagnetic force, charged particles can interact with each other by exchanging photons. For example, when an electron and a positron, the antiparticle of the electron, come into contact, they can annihilate each other and produce 2 photons. Similarly, a photon can be absorbed by an atom, causing one of its electrons to jump to a higher energy level. When that electron falls back down to its original energy level, it emits another photon with the same energy as the absorbed photon. Photons are unique among the particles of the Standard Model in that they have 0 rest mass. This means that they always travel at the speed of light and cannot be at rest. Photons also have the spin of 1, which means that they have an intrinsic angular momentum. The photon was first proposed as a particle by Albert Einstein in 1905, as part of his theory of the photoelectric effect. This theory explained how electrons are emitted from a metal surface when light is shown on it. Einstein proposed that light was made up of discrete packets of energy called photons, each with a frequency and energy proportional to its wavelength. This idea was later confirmed by experimental evidence, and it became an important part of the foundation of quantum mechanics. In the Standard Model of particle physics, the photon plays a crucial role in mediating the electromagnetic force, which is one of the 4 fundamental forces of nature. The other 3 forces are the strong nuclear force, the weak nuclear force, and gravity. The photon is responsible for the behavior of electric and magnetic fields, and it interacts with charged particles such as electrons and protons. Overall, the photon is a fundamental particle of nature that plays a central role in the theory of electromagnetism and the Standard Model of particle physics. Its discovery and subsequent understanding have had a profound impact on the field of physics and on our understanding of the behavior of matter and energy at the smallest scales. Quarks and gluons are the building blocks of protons, neutrons, and other hadrons. They are elementary particles that are considered to be the fundamental constituents of matter. The theory that describes the behavior of quarks and gluons is called quantum chromodynamics, QCD. Quarks were first proposed as fundamental particles in 1964 by physicists Murray Gell-Mann and George Zweig. They independently suggested that protons and neutrons, which had been known to be made up of smaller particles called nucleons, were in turn made up of even smaller particles, which they called quarks. Gell-Mann and Zweig's ideas were eventually combined into what is now known as the quark model. Quarks are classified into 6 different flavors: up, down, charm, strange, top, and bottom. These flavors are distinguished by their mass and electric charge. Up and down quarks are the lightest and most common flavors, and they are the ones that make up the protons and neutrons in atomic nuclei. The other 4 flavors are much heavier and are found only in high-energy particle collisions. Gluons were also first proposed in the 1960s as part of the theory of quantum chromodynamics. They are the particles that mediate the strong nuclear force, which holds quarks together inside protons, neutrons, and other hadrons. The strong nuclear force is one of the 4 fundamental forces of nature, along with gravity, electromagnetism, and the weak nuclear force. Gluons are themselves elementary particles, and they come in 8 different colors. These colors are not related to the colors we see in everyday life, but rather they are a way of describing the interactions between quarks and gluons. Quarks can be red, green, or blue, and antiquarks can be anti-red, anti-green, or anti-blue. When a quark and an antiquark interact, they can exchange gluons, which can be colorless combinations of the red, green, and blue colors. This color exchange is what allows quarks to interact and form bound states like protons and neutrons. The discovery of quarks and gluons has been confirmed through numerous experiments over the years. In 1968, experiments at the Stanford Linear Accelerator Center, SLAC, in California provided the first direct evidence for the existence of quarks. Since then, experiments at particle colliders around the world have continued to study the properties of quarks and gluons, including their masses, charges, and interactions. In conclusion, quarks and gluons are elementary particles that are the building blocks of protons, neutrons, and other hadrons. They were first proposed in the 1960s as part of the quark model and quantum chromodynamics, and their existence has since been confirmed through numerous experiments. The study of quarks and gluons continues to be an active area of research in particle physics, with important implications for our understanding of the nature of matter and the universe as a whole. Neutrinos are fundamental particles that have no electric charge and very little mass. They are one of the most abundant particles in the universe and are produced in a variety of natural processes, including nuclear reactions in the sun and supernovae explosions. Neutrinos were first proposed in the 1930s by physicist Wolfgang Pauli as a way to explain the apparent violation of energy conservation in certain types of radioactive decays. According to the laws of conservation of energy and momentum, the energy and momentum of the particles involved in a decay should add up to the same values before and after the decay. However, in some cases, it appeared that some energy was missing, suggesting that an unknown particle was being produced that was carrying away some of the energy. Neutrinos are extremely difficult to detect because they interact very weakly with matter. They can pass through vast amounts of material without being absorbed or scattered, making them very difficult to detect. However, there are a few processes that can produce detectable signals when a neutrino interacts with matter, such as the production of charged particles or the emission of light. The study of neutrinos is important for a number of reasons. First, neutrinos are produced in many natural processes, including the fusion reactions in the sun that provide the energy for life on Earth. Studying the properties of neutrinos can therefore help us understand these processes and the behavior of stars and other astronomical objects. Second, neutrinos play a key role in particle physics. They are produced in many high-energy particle collisions, and their interactions can provide important clues about the behavior of other particles and the fundamental forces of nature. Finally, the study of neutrinos has important implications for our understanding of the universe as a whole. Neutrinos are thought to have played a key role in the evolution of the universe, and studying their properties can help us understand how the universe has changed over time. Neutrinos were first detected experimentally in the 1950s by physicists Frederick Raines and Clyde Cowan, who used a large tank of water to detect the particles produced in a nuclear reactor. Since then, many other experiments have been conducted to study the properties of neutrinos, including their masses, flavors, and interactions. In conclusion, neutrinos are fundamental particles that are extremely difficult to detect because they interact very weakly with matter. They are important for a number of reasons, including their role in natural processes, particle physics, and our understanding of the universe. Neutrinos were first proposed in the 1930s and were first detected experimentally in the 1950s. The study of neutrinos continues to be an active area of research in particle physics and astrophysics. The electron is a fundamental particle of matter that carries a negative electric charge. It is a subatomic particle, which means it is smaller than an atom, and it is a building block of matter, along with protons and neutrons. The importance of the electron in particle physics cannot be overstated. It is one of the most widely studied particles in physics and has played a significant role in the development of the field. It was the first subatomic particle to be discovered, and its discovery helped to pave the way for the development of modern particle physics. The electron was discovered by J. Thomson in 1897 while he was conducting experiments with cathode rays. Cathode rays are streams of electrons that are emitted from the cathode of a vacuum tube when an electric current is passed through it. Thomson observed that the cathode rays were deflected by magnetic and electric fields, which led him to conclude that they were made up of charged particles. Thomson went on to measure the charge-to-mass ratio of the particles and found that it was much smaller than that of any known atom. This led him to conclude that the particles were a new type of fundamental particle, which he named electrons. The discovery of the electron revolutionized our understanding of matter and helped to lay that groundwork for the development of quantum mechanics. It also played a critical role in the development of electronics, as the flow of electrons is what drives electrical current. In particle physics, electrons are important because they are one of the fundamental particles that make up matter. They are also one of the lightest particles, and their properties have been studied in great detail, providing important insights into the behavior of subatomic particles. Overall, the electron is a fascinating and essential particle in the world of physics, and its discovery has had far-reaching implications for our understanding of the universe. The W and Z bosons are elementary particles that mediate the weak nuclear force, which is one of the four fundamental forces of nature. They were first predicted by the ultra-weak theory developed by Sheldon Glashow, Ed Solom, and Steven Weinberg in the 1970s, and their existence was later confirmed by experiments at the Superproton Synchrotron (SPS) at CERN in the early 1980s. The W and Z bosons are extremely heavy particles, with masses of around 80 and 90 times the mass of a proton, respectively. They are also electrically charged, with the W bosons carrying a positive or negative charge, and the Z boson carrying no charge. The importance of the W and Z bosons in particle physics lies in their role as mediators of the weak nuclear force. The weak force is responsible for processes such as beta decay, where a neutron decays into a proton, an electron, and a neutrino. The W bosons are responsible for this decay process, as they can change the flavor of quark, which is one of the building blocks of protons and neutrons. The Z boson, on the other hand, is responsible for neutral weak interactions, such as the scattering of neutrinos off atomic nuclei. The discovery of the W and Z bosons was a significant milestone in particle physics, as it confirmed the ultra-weak theory, which unified the electromagnetic force and the weak nuclear force into a single force. This was an important step towards the development of the standard model of particle physics, which describes the behavior of all known elementary particles and their interactions. The discovery of the W and Z bosons was made possible by the development of high-energy particle accelerators, such as the SPS at CERN, which allowed physicists to study the behavior of particles at extremely high energies. The experiments involved colliding protons and antiprotons at high energies and measuring the particles that were produced in the collisions. Overall, the W and Z bosons are crucial particles in particle physics, and their discovery was a significant step towards our understanding of the fundamental forces of nature. They continue to be studied extensively today, both through experiments at particle accelerators and through theoretical research. The graviton is a hypothetical elementary particle that is postulated to be the carrier of the gravitational force, which is one of the four fundamental forces of nature. It is the quantum particle associated with a gravitational field and is believed to be responsible for the interaction between objects with mass or energy. The graviton was first hypothesized in the 1930s by physicists Paul Dirac and Feck, but its existence is still unproven. While the other fundamental forces have their respective particles, such as the photon for electromagnetism, the W and Z bosons for the weak force, and the gluon for the strong force, the graviton has not been directly detected or observed experimentally. Despite this, the graviton plays a significant role in the study of particle physics and the fundamental forces of nature. Its existence is predicted by the theory of general relativity, which describes the behavior of gravity in terms of the curvature of spacetime. The graviton is the particle that mediates the gravitational force, allowing for the exchange of energy and momentum between objects with mass or energy. The importance of the graviton in particle physics lies in its role in unifying gravity with the other fundamental forces of nature. While the other forces have been successfully unified under the Standard Model, gravity has yet to be incorporated into this framework. The existence of the graviton would provide a bridge between the macroscopic world of gravity and the microscopic world of particles, allowing for a more complete understanding of the universe. Despite its importance, the graviton remains one of the most elusive particles in particle physics, and its existence has yet to be confirmed. However, its continued study remains a crucial area of research in the field, as it has the potential to unlock new insights into the nature of the universe and the fundamental forces that govern it. The Standard Model of particle physics is a theory that describes the behavior of all known elementary particles and their interactions through three of the four fundamental forces of nature: electromagnetic, weak, and strong. The mathematics behind the Standard Model is highly complex and requires a deep understanding of various mathematical concepts and techniques. In this response, I will provide an overview of some of the key mathematical ideas that underpin the Standard Model. Group theory. One of the most important mathematical concepts used in the Standard Model is group theory. A group is a mathematical structure that describes the symmetries of a system. In the case of the Standard Model, groups are used to describe the interactions between particles and the symmetries of space and time. The Standard Model relies on two main groups: the SU-3 group for the strong nuclear force and the SU-2U-1 group for the ultra-weak force. Quantum field theory. Another key mathematical concept used in the Standard Model is quantum field theory. This theory describes the behavior of particles as waves that propagate through space and time. The mathematics of quantum field theory involves manipulating complex functions known as quantum fields, which describe the interactions between particles and the forces that mediate those interactions. Feynman diagrams. Feynman diagrams are a graphical representation of the calculations involved in quantum field theory. They depict the interactions between particles in a particular process, showing the particles involved and the forces mediating those interactions. Feynman diagrams are a powerful tool for calculating the probabilities of various particle interactions. The Higgs mechanism. The Higgs mechanism is a key component of the Standard Model that explains how particles acquire mass. The Higgs mechanism relies on the existence of a scalar field, known as the Higgs field, which permeates all of space. As particles move through the Higgs field, they interact with it, causing them to gain mass. The mathematics of the Higgs mechanism involves complex calculations of particle interactions and the behavior of the Higgs field. Overall, the mathematics behind the Standard Model is highly complex and requires a deep understanding of various mathematical concepts and techniques, including group theory, quantum field theory, Feynman diagrams, and the Higgs mechanism. The mathematical framework of the Standard Model allows physicists to make predictions about the behavior of particles and their interactions with a high degree of accuracy, allowing for the development of new technologies and a deeper understanding of the fundamental forces that govern the universe. Goodbye.